viewers, good afternoon, ladies and gentlemen. A cordial welcome from the International Space Science Institute to its Game Changer seminars. My name is Megha-Tropiques. I'm the director for Earth Sciences at ISI. And today we have the 5th edition of our seminar series, Viewing Earth from Space, the Changing Environment and Climate of Our Planet. I'm very, very happy to be able to welcome Dr. Rémy Roca today. Rémy is Director of Research at the CNRS, the French National Center for Scientific Research, where he is with LEGOS, which is a Laboratoire d'études et géophysique et océanographie spatiale. Rémy is a very well-known person. He's been the principal investigator of the Megha-Tropiques mission for the last 15 years, and he's been involved in various Earth observation missions from space, which are related to the energy and water cycle. Rémy has been with the Scripps Institute for Oceanography in La Jolla and with the Laboratoire Dynamique Atmosphérique LMD in Paris. And he's been, meanwhile, over 130 publications calling his own, including 75 papers in renowned journal. He has been in the helm in writing several books, which are for general audience on climate change and satellite observations, and he's strongly involved in the coordination group for meteorological satellites and the World Climate Research Program. Rests me to say that we are very happy to have Rémy here today to give the seminar on water and energy cycle from global to storm scales, a very, very relevant research topic in our area. Before I hand the floor to Rémy, I would kindly ask the audience, in case you have questions during and after the presentation by Rémy, please put them in the chat and I will try to moderate them subsequent to Rémy's presentation. With that, I think all is said, and I'm very happy you're here, Rémy, and over to you. The floor is yours.
Okay, thank you very much, Michael. So it's my pleasure actually to be part of this seminar series that ISI has been running for some time now. I think it's a very interesting and unique opportunity for us scientists to discuss our research and to share our approach towards some scientific question with the common tool that is the space-based observation capability. And so today, this is exactly what I would like to do during this presentation, is to focus my presentation on water energy cycle, as you said, but I will at the same time try to deliver you some very recent scientific results. Some are published and just last month, some are not even yet published. But at the same time, I would like to take the opportunity to also explain how we approach this research. And so I will get started with a very basic consideration on how we can deal with this a very exciting topic of water, energy, and climate change before I go into more research-focused results that I would like to share with you. Before going through the presentation, I would like to acknowledge a number of my colleagues that I've listed here, with whom I'm having a very genuine interaction on various questions ranging from remote sensing to differential equation solving or more on climate change basic discussion. So with this little introduction, let me move on to where exactly I think our work is actually belonging. So this is the general picture of the planet Earth next to the sun. And I took that illustration from a textbook that clearly shows all the various dimensions that you can do when you're doing geophysics as a broad topic. And today, and in my research, I'm not focused on all those aspects of geophysics, but only on the first number 1, 2, and 5 actually aspect of that. We are going to look at how the sun is influencing the climate, and how the Earth is going to balance the solar input through a radiation exchange. So just to show you, it's only part of the story of geophysics, but we are going to stay focused on those red area for today. And so to get started, I just want to say, once you're set up in this framework of the Earth being in space, you can apply some very basic principle of thermodynamics. And we usually tend to neglect some work from Earth on space, and we end up having this statement that Earth exchange energy with space only through radiation. So that's a very important point, that the exchange of energy is taking place through radiation only, as the time scale we are concerned. And so if you consider a steady state of the Earth, we can call it equilibrium. I like this kind of vocabulary, although some people prefer a different way of saying that. But in a steady state, the energy emitted and reflected by the Earth has to equal what is got from the sun. That's basic thermodynamics applied to a planet. And it is possible that an imbalance occurs in this equilibrium, and then the system is no more in equilibrium. And so the Earth is going to react as to restore the initial balance. And this is what we call climate change, actually, is to try to cope with the imbalance at the top of the atmosphere. If you take a very famous example, atmospheric concentration of CO2 increase will cause a positive imbalance at the top of the atmosphere. And so the full Earth will have to warm to restore the balance. And that's what we are trying to now navigate with our model and our satellite observation as a big societal question, but also a big scientific question. So the Earth is not only a planet, it's a planet with an atmosphere, if I can say so. And so the difficulty is how those radiation exchange with space are taking place, and how we can relate what's going on separately in the atmosphere and the surface. And so that's the major question, is how we can relate those first principles at the top of the atmosphere to what's going on at the surface. So I took this little illustration from an old paper by Professor Ramanathan, which is basically telling us in a nutshell how the water vapor feedback is going to influence those exchange with the space, the radiation exchange with space. So in the first case, the little number 1, I think you can see my mouse here. So you have a direct forcing of increased CO2 concentration in the atmosphere. This is going to create a small surface heating by direct greenhouse effect on the top of the surface. This surface heating is going to trigger some perturbation of the water cycle. In particular, in this framework, we can easily relate it to an increase of evaporation. This will provide more water vapor molecule for the atmosphere to hold, and this increased humidity in the atmosphere, because the water vapor is a very powerful greenhouse gas, is going to also change the long wave emission, or the infrared emission, as they used to say in the 80s. And this will contribute to an enhanced warming. And this is a very infernal loop, if you wish, where you have an initial condition that is going to be actually triggering a perturbation which is going to be enhanced by itself. So it's a very positive feedback loop that is drawn here, and that is going to influence how the top of the atmosphere exchange with the sun or with the space are going to be realized. There is a second consequence of adding CO2 in the atmosphere, is the number 2 here. It's called a direct tropospheric heating. So the atmosphere warms not only the surface when you increase the CO2 concentration, and that is tends to amplify the feedback loop that I just mentioned. So the processes by which this new equilibrium after an imbalance is caused is achieved is strongly involving water energy feedbacks in the Earth and atmosphere surface. And finally, there's a third impact of this perturbed water cycle, is that because you put more water vapor molecule in the atmosphere, you end up having more precipitation at the end. And this precipitation in the atmosphere is also contributing to the warming of the atmosphere, and also contributes to the amplification of the feedback. So this is with the hands how the processes involving water vapor and water in the atmosphere can play together to influence the radiation. And so I want now to pay a little tribute to a famous scientist in our field, because he was the key person to actually try to promote very early on in the pioneer work what are the quantitative consequences for surface temperature of all the processes that I just highlighted for respect to the water and the water vapor feedback. So Manabe did a seminal contribution, which I'm going, unfortunately, to resume in one slide. So please bear with me for this. And if you have interest in a more refined understanding of the contribution of Manabe to our field, I would suggest to go and read those two little commentary pieces that I found very enlightening about how to put in perspective the work of a single scientist in the early 60s back into what we do today. And but just to make sure that I can relate what I just said before to this work, the strong contribution of Manabe, as far as I understand it, is to have promoted a new theory based on those first principles, that we call radiative convective equilibrium. So in the radiative convective equilibrium, you try to understand both how the radiation and convection are going to redistribute vertically the energies to achieve the balance at the end with space. And there is an example on the left here of a profile of temperature, which is drawn from the surface here to the top of the atmosphere. And you see there are two main results over here. The green curve, which is here, it's called the pure radiative equilibrium response of the Earth, which is what people tend to be doing since 4 years' time, is to compute the surface temperature, assuming some exchange within the atmosphere, but neglecting anything other than radiation. And so the very strong insights of Manabe could be resumed in this one bullet here, is the vertical transport of energy due to convection. Here, instead of being computed, it's just specified. The 6.5 degree per kilometer adjustment is the actual net result of convection, and that's which is based from observation, actually. And so by doing this, he was able to really improve significantly the computation of the surface temperature and link in pink here the convection, the surface temperature and the vertical profile to the equilibrium radiation. So the main outcome of this mid-60s work is that the surface temperature is actually controlled by the top of the atmosphere energy balance, as I was mentioning, and not the surface energy balance. It's a strong conceptual move. And of course, to realize that convection cools the surface was something that people didn't have so much of a perspective before. And in the second time, Manabe and his collaborator explore the sensitivity of this new framework to CO2 increase or decrease. Actually, back in then they were doing decrease and increase CO2 experiments, and in order to provide the correct perspective on the water vapor feedback that I've just shown you the processes before, he made this very unique assumption called relative humidity is constant. It's based on actual observation by radio sound from the 50s that from one season to another in the atmosphere, the relative humidity doesn't change much. So I assume it was constant. And by doing those, he was able to do the first estimate of the climate sensitivity. That is the response of the surface temperature to an increase by 2 times of CO2 concentration, including a proper description of the water vapor feedback. And this is the result on the right here with the so-called fixed relative humidity assumption, where you get a response around 2 to 3 Kelvin per doubling of CO2, compared to the previous assumption people were having, where they were not considering the change in humidity, actually. And he was able to quantify for the first time the fact that water vapor feedback could double the climate sensitivity. And that's a very major advance in our understanding of how all of this works. And probably I could go on longer on the strong contribution of this scientist, but I just want to show to connect the fact that what we are going to discuss today is rooted in some basic physics that just got acknowledged recently. So there's not only consequences of those first principles on surface temperature, there are consequences on surface precipitation. So if you look at this little diagram that I took from a paper by Graham Stephens a few years back, where you see all the fluxes that goes into the surface and the atmosphere of the Earth and goes back to space. What we are going to look at here is not as previously the top of the atmosphere budget, but the surface budget, and I'm going to make it very simplified. I'm going to put all the radiation-based term into a single term, which I'm going to call air net at the surface, and I will assume that at equilibrium there is a balance between the radiation and the sensible heating, which is here, and the latent heating at the surface. So by writing my surface budget like this, I am able to start to compare how precip and radiation at the surface are going to interact. And so because I still follow the relative convective equilibrium assumption of Manabe, we can rewrite the net at the surface as being equal to the net loss of energy in the atmosphere. And I can further split that into clear and cloudy. So I'm going quick, but it's not a I could always answer question after if you want, because the clear, as I just clear sky, as I just mentioned a couple of slides ago, is very straightforwardly related to the water vapor content here, W. Okay, so it's possible to express the relative loss in the atmosphere related to the water vapor content. And following Manabe assumption of relative humidity being constant, we clearly are going to see that W, the water vapor amount, is going to increase with temperature. And actually, we have a very strong constraint also from thermodynamics on this through Clausius-Clapeyron. And we know that this water vapor amount is going to scale at the Clausius-Clapeyron rate around 7% per Kelvin warming. If you do the little mathematics, you will find that this turns into the net clear atmospheric loss changes per warming, per Kelvin warming is about 2 to 3% relative change. So, so the relative cooling is going to change by 2 or 3% per degree warming. If you go back to my surface budget equation and do the neglecting of clouds, and you remove the sensible heat flux, which is a small term, and at this stage, we are not very concerned about all of those middle terms, you will see that you can clearly easily show that the precipitation scales as the relative cooling. And so that gives you, out of this relative convective equilibrium theory and the basic principle of thermodynamics, a strong constraint on the possible increase in precipitation that is probably going to be between 2 and 3% per Kelvin warming. So in a nutshell, I wanted to emphasize the fact that we have a very physically sound framework analysis to proceed into more detailed investigation. And so as an observationalist myself, I am keen to elaborate on this kind of question. What is the observational constraint that we can provide on those first principle considerations? And of course, using satellites, which are so well suited to actually study the planet. So really, I would like to say, do we have an observational constraint of those theoretical consideration? How can we articulate that? So I say that because, as you are very familiar, there are a bunch of satellite observations dedicated to the global water energy cycle. I have listed on the table all the 13 fluxes that goes into the little diagram that you've seen. And on the right side, you can see that there is a bunch of mission names. I have only highlighted a few, but you probably know some of those, or maybe you know some that I didn't mention, but are relevant to this problem. So you see that as far as the radiation at the top of the atmosphere is concerned, we rely on a combination of data from CNRS, MODIS, geodata, geostationary data, but also source for the sun monitoring, for instance. As far as the surface is concerned, the precipitation can be derived from this GPM, or Global Precipitation Mission Constellation, or the microwave imager. For the latent heat flux and the sensible heat flux, you tend to combine IR with microwave, and so on and so forth. And more recently, thanks to the big effort of of all the people involved in the altimetry and the gravimetry science, we are also able to get a constraint on the ocean heat content or the Earth energy imbalance by combining gravimetry and altimetry measurement, so that those recent advances of the satellite observing system and how we turn those raw data into essential climate variable permit us to explore now almost entirely satellite-based depiction of the global water energy cycle, fluxes and stocks. And so this is what I want to do now, is to say, okay, we have the capability, how can we provide a constraint? And so before getting into detail, I just want to highlight only a single exercise of what we do now in the PRECIP world, because most of those products that I listed just before, they can have a very elaborated algorithm behind them, or even observing technique related to them. Here, it's a little video over what's going on in 3 hours over the Earth when you are using the full constellation of microwave imager and sounders, plus the GPM core or radar satellite, to estimate precipitation, which is a highly intermittent field. So we need a heavy sampling to put our hands on the quantitative aspect of PRECIP. And we are able now to develop a very advanced algorithm and product like this. And this is one example. I could have taken radiation or evaporation, but I have my own bias, as you can guess, on the PRECIP world. But unlike like most of the data sets we tend to play with, like precipitation, all those ECV are developed independently of each other. It's what we call a silo. Precip people do precip, and radiation people do radiation. And eventually, we hope at the end that they all come together to help us closing the budget of the water and energy at the global scale. And this is an effort I took from a paper, a very important paper by my colleague Tristan Lécuyer, from a few years ago, where he basically took what was available back then over a 10-year average and tried to look at those fluxes from space-based mission. And there was a big issue. They are not closing at all the Earth radiation budget. We are actually having a 16 watt per square meter imbalance on the so-called base data set from that time, which is 20 times too big. So that's totally not physical. So that's a very dramatic conclusion, because this improvement and how to be quantitative about the water energy cycle from space is a long-term research goal of the WCRP, and in particular of the JWEX core project, where we have done a lot of remote sensing development over the years, and we have tried to do some adjustments sometimes to try to better close that. Eventually, what came out of those analyses is that a new paradigm is needed. And now, instead of looking at closure, we're going to enforce closure, and using the conservation law that we are familiar with from the earlier work and the pioneer work on the basic principle of physics applied to the Earth. And we're going to explore whether it's consistent with our product within the uncertainty bar, or the error bar, if you want. So we are going to shift gear from estimate to closing the budget to enforcing the closure and exploring the consistency. So it's a nice evolution of the perspective on how to deal with that data set. And of course, what we want out of this is to use objective technique to do this this mixing of and optimization of the data set. So there have been quite a lot of effort, some supported by NASA from the paper by Tristan and Matt, and also some effort were supported by ESA on a more water budget perspective, and maybe less global, but at least over some large catchment. So we have been seeing over the last few years some effort to implement objective technique to explore the consistency of our data set after enforcing closure. So we have been doing the same in our group together with my colleague Benoît Messignac and a few others. So I'm not going to go into detail. What I can tell you is that we write the various budget equation as I did in my introduction. This time we are trying to separate what's going on over land, over ocean. We do also the water separately from the energy budget. We look at the storage term in the subsurface and so on and so forth. And as I mentioned here, we use this global scale constraint Like, for instance, there is no net storage of energy at the continental surface, and the net equivalent for the ocean is the time derivative of the ocean heat content, which we set to 0.6 watt per square meter right now. So with those constraints and some optimization techniques, so I'm not going to go into detail of that. First of all, it's not where I am the most relevant, but I just want to show that there is an effort to use this kind of methodology. Here in our group, we're using a least square generalized framework to do the optimization of the cost function. But the takeout message I want to put here is that when you get into this level of quantitative aspect of the data, what is very important is to characterize the uncertainty that goes along with the actual value of the observation. And this is something where I think the Earth observation remote sensing community has been a bit shy in the past. We tend to do our best for our product, but we still need to do a strong effort to better characterize the associated uncertainty so that we can benefit from this kind of objective technique. So once you plug that in, and now I'm not going to use anymore the Lequi et al. Data, I'm going to actually use a newer data set called the GeoX integrated product data, which has been developed over the last 10 or 15 years. It's a long-term effort of trying to provide those observations and their uncertainty characterization. So GeoX is part of the WCRP, and it's a long-lasting effort of GeoX to try to put numbers on those kind of diagrams. And here it's the outcome of a paper which is actually in review in BAMS. It's the 30th anniversary paper of GeoX Science that is led by Graham Stephens, for which we provided this little cartoon. So in this cartoon, we have already applied the optimization. And so, as you can see, we have precipitation and evaporation are now consistent. They were not before we do the adjustment. And we can see how things are getting all together. So we have the radiation and the Earth energy imbalance, which now agrees, which is because we are enforcing that. And it is consistent with the actual uncertainty we have on both the solar and the outgoing long-wave radiation at the top of the atmosphere. And even the surface budget seems now to be consistent within the original uncertainty of the data set. So what I want to point out a few things on this diagram is the fact that on the radiation, we are still chasing some small value, alpha watt, but we do have a large number that cancel together with a relatively good uncertainty. It's only a 1% here. Of course, on the incoming solar radiation, this is a very strongly constrained variable by the observation. So we have a very, very small uncertainty that provides a strong constraint to the whole system. And we see also that on precip and evap, we are still having almost a 10% uncertainty at the end of the optimization effort, which is one of the weakest set of product together with sensible heat, for which the uncertainty remains extremely high for various reasons that I'm not going to discuss now. But since it's a smaller term in the budget, it doesn't really change too much the full story. So anyway, now using this kind of technique and this kind of data set, we are able to get a better and consistent perspective on the energy balance in the atmosphere and at the surface. So as the seminar came, I thought it would be nice to go beyond just this kind of documentation of the actual water and ice cycle, and to say, okay, now that you pretend to have a better data set, what does it tell us about the theory? Do you have the constraint? So this is work in progress that I'm sharing with you. It's from a student working in our group with Benoit and myself. It's Robin, who is a PhD student at Lagos, who has been looking at the difference between two periods of 5 years to estimate how the relative rate of change in percent per Kelvin is quantified and constrained by those observations in blue. And he compared that with what I would call the latest incarnation of Manabe's work from the SEMI-6 exercise, all the model in pink. And so you see on the left, you have the list of the product of the fluxes that have been considered. And in pale blue, we have the data before we do anything to them. And in a darker blue, this is after we have applied our optimization scheme, after we have made them consistent. So if you look in the bottom of the plot, you can see the strong impact of this optimization on precip. So, and here I forgot to say, I'm sorry, I'm using a third data set. It's no more the L'Écuyer NASA News one. It's no more the GeoX one. It's a Copernicus Climate Change Service data store, because that study was funded through a Copernicus project. And so we were exploring how the European data store was actually performing in that framework. So if you look at the bottom for precipitation, before any optimization, we over that 10-year period, the rate of change was quite high, more than 4% per Kelvin warming. That seems to be high compared to the theoretical guidelines, but it was much, almost 3 times, 2.5 times more than the model. So that would be an interesting output if the model were so wrong. But eventually, once we did the consistency analysis, we are able to cool down this precip trend to something more closer to what we were expecting, around 2% per degree warming. As you can see, the evaporation is now very consistent with that precip. And the model, who are also very consistent, as you can see by definition, are actually just close by the observation and may just lack alpha % or 1% of sensitivity. But it's much more consistent now to assess the evaporation and the precipitation of the model, and we probably need to explore in more detail why the model do have such a lowest sensitivity over that very specific time framework. If you look at the other fluxes, I'm not going to go into all the detail. You see that there is some area also where the optimization has benefited the comparison to the model. For instance, for sensible heat, in the raw data, there is almost no sensitivity, while now we are able to showcase something similar to what the model sees, a decrease of a couple of % per Kelvin. We are still seeing some issue in the model, which are now clearly coming up on the shortwave at the TOA on that surface. We need to relate that now to how the aerosols are processed, or what various aspects of the inside of the atmosphere. But this is work in progress I wanted to share with you, because I really want to share with you where we are going. And so we are reaching the point where we can really see that we are about to provide a space-based observational consistent constraint on water energy cycle evolution that is relevant to the physics I highlighted earlier, and that is probably also relevant for the model evaluation. So as I was going through my slide, I think you realize that there's a lot of clouds in the middle that I didn't mention so much so far. But as a way to articulate to the second part of my presentation, I would like to recall how deep convection is a very important process in the water and energy cycle. So deep convection is basically a transport. Convection is a transport mode. If you hit the bottom of your cooking pan, you will trigger some convection cell. But if you do this in the atmosphere, where you have atmospheric humidity and a temperature decrease with the vertical, you end up condensing some of the material as you transport it upwards. And what you end up building is that deep convection builds a deep convective cloud, which I have shown you here on the picture, which I took when I was a student. Back then, I was able to do some field work, and I was on a campaign in the ocean, Indian Ocean, during the winter. And when we were crossing the ITCZ at almost like 0 degree at the equator, we were able to see this big, nice development of convective storm that I was already interested in back then. And so this convective process interacting with the water vapor in the atmosphere and the temperature is going to build a cloud, which is going to interact with radiation, and also to produce precipitation by condensation, which I already mentioned. So it's important to recall that a lot of those fluxes are connected through a process, and one of the lead processes is the convection. And it happens so that we would like to have the same kind of approach again. Can we say something relevant to the discussion concerning the convective part of the relative convective equilibrium using our satellite perspective? So first of all, I'm going just to be very quick on how convection, how does it look like a convective storm or a deep convective cloud system. They do have various names, and I'm sorry for that, but sometimes we do mix a lot of meteorology, climate, and thermodynamics, so it becomes uneasy to follow. But so in today's presentation, I will stick to storm or to cloud system or convective cloud system. So on the right, you have a vertical view from almost above, from an angle, that is show you the distribution of hydrometeors in the atmosphere when you have a convective storm acting. So in gray, you have the cloud condensate distribution. So you see a very nice cloud, which has a shape of a anvil, if you really want to have it in mind. And inside that, we can see from this nice illustration, all the convective cell acting as transport, as a way to transport the water vapor upward and to build that cloud condensate. So the yellow is the updraft and the blue are the downdraft part of the convective cell I was highlighting. So just to give you a scale, the cloud shield can be up to 1,000 kilometers, but the process, the updraft, is 1 kilometer. So that gives you the scale that we are dealing with. A few convective cells are building a huge cloud deck. So that's something to keep in mind. And what is interesting also is that this cloud deck from above, from a satellite perspective, we've been observing them since the beginning of the observing era. And this is here a much more recent view from Imawari. It's a geostationary from Japan and from GMA and JAXA that is observing mainly the Western Pacific region. And here it's an example I'm going to show you of this imagery. It's next to the warm pool. And it's a couple of days where there is a hurricane activity. And here the color coding is a bit unique. In red, it's very cold. As you get redder, it's cooler, which means deeper in the atmosphere. And the blue is the warm ocean below. And of course, those storms, they don't just pop up organized with a large deck. They start as a tiny little object that grows and eventually dissipate. They do have a very nice life cycle that this little video is going to show you. So you can see from a basic meteorological satellite observation, I think we do have a very deep record of those observations. In my group, we are working now with the EUMETSAT FCDR of Meteosat, and we go back almost continuously from nowadays to 82 with imagery like that every half an hour, providing us the cloud deck information. And so once you have this kind of cloud deck data, you can plug in what we call a pattern recognition and tracking algorithm that is going to give us access to a quantitative aspect of the morphology of the upper level cloud shield. So you have a little example on the right where each of the color represent a single individual system that has been identified by the algorithm in this moving imagery. So I won't go into detail on how it works, but it's a nice technique that is trying to cope with the difficulty of doing this kind of analysis by hand. So, so with this, we call it Toucan for tracking of organized convection with the 3D segmentation. And again, I don't have time to go into detail, but it has been used for a couple of almost a decade now, and it has been shown to be useful to this objective characterization of the morphology. So based on that, we asked the question: Can you tell us something about the cloud physics using your morphology information that you derive from the satellite? And so for that, we say, okay, we are going to look at the growth rate of the cloud shield when the storm is growing or decaying. The shield of this cloud may be evolving in a way that is related to the physics. So we've done a very simple model, very idealized model of this cloud shield growth rate. We call A the shield area. AC is the convective part of that, which is much smaller, as you can remember. And we have a term which I'm going to describe quickly called the convective mass flux, which is the vertical transport of mass by convection. And that will be the source term of our simple model. And of course, we have a sink that is removing condensate from the storm that we just relate by a very simple relaxation time that we call tau. So when you start to implement this kind of simple model, you realize that you can relate the mass flux, to the vertical velocity. And I'm not going to go into detail, but I just want to emphasize that by using the first time principle and the conservation of static energy and an equation of continuity applied at the cloud scale this time, not at the planetary scale, but at the cloud scale, we can approximate this very hard to measure vertical velocity parameter thanks to the latency profile, latency release profile, and the lapse rate, which is the vertical gradient of temperature in the atmosphere as a proxy for some instability. So we get this very simple relationship that we can inject in the model, and we have this pink equation, which is our equation of evolution of the cloud shield. And so what we end up, we have been recasting this equation into a much more simpler one, where we are only going to look at the maximum of the profile of this source term, not the full distribution in the vertical, and using a bunch of observations from various satellites and multiple instruments. In synergy, we are going to estimate all of those terms. So the growth rate is constrained by toucan and the geostationary data. The GPM, dual precipitation radar, dual frequency radar, give us a good estimate of whether there is or not deep convection in the storm. And it also gives us a very nice product of the latency profile distribution in the atmosphere that we can use to inform our equation. And we relied on the Earth profile of temperature and relative humidity. Earth is it's an infrared, hyperspectral instrument that has been providing interesting sounding capability over the last decade. And so we are merging all of those data to assess the capacity of this simple model to represent the reference that is here. And we are very happy with the results, which are shown here for various classes of storm, but you can just look at this very last one here, the little H figure. So you have the predicted on the y-axis and the actually observed growth rate. So when it's positive, the system grows. When it's negative, the system decreases in size and dissipate. And you can see that we have a pretty good fit. So out of this, we were happy because it means that the functional form of the simple model is actually reasonable to the scale we are looking at. And we have been looking at the two fitting coefficients in more detail. And the fact that beta 1 is very close to 1 translates into the fact that this approximation of the mass flux convergence into a diabatic heating term seems to be not too unrealistic. And we were very surprised by the beta 2 coefficient, which turns into a very intense sink for the cloud condensate compared to the literature. And so we think the explanation comes from the fact that we are tracking the cloud here. So we are within the cloud. And so it's a bit different from what has been reported previously that was more focused on grid area. So thanks to this model that we have been validating using data and informing with data, we are now able to invert the equation and answer the question, do we know the threshold by which how much convective activity is needed for the system to grow, which has been a question for various model and cloud parameterization in the past. And so by just inverting our little equations, you find that when there is more than 10% of the storm that is due, which is convectively active, it is growing, while if it's less than 10%, it's going to decay. So by merging all of those data onto a little set of equations, we were able to promote a new constraint at the process level on the cloud growth rate, which is at the heart of some of the discussion of the early part of my presentation. So now I'm about to end my presentation. I just want to walk you towards what we plan to do in the future, because we are having a quite a busy programmatic as far as the water energy cycle and deep convection is concerned, because we got the very nice news last fall that one of the mission that was submitted to one of the NASA call, a very research-oriented mission. Was selected actually, so it is budgeted with $160 million plus launch, and this mission is going to be building on miniaturized radar and what we call new space technique to build a convoy of 3 radar, which are going to be just next to each other by 30 to 90 seconds, as drawn on my little cartoon. And the full idea is that we are going to use the time derivative of the 2 snapshots to actually transform the 2 snapshots into a velocity. And we are now building the algorithm to retrieve vertical velocity at the cloud convective scale in the convective cells using the time derivative of those 2 snapshots of those 2 small radar. And so the funny part of the story is that the proposal was submitted when we sent it. It was called D-Train, and when it was accepted, it was called INCUS. So now it's INCUS, but I don't even know what INCUS stands for because I was still in the D-Train world. But I just want to say that INCUS, the cumulonimbus INCUS, is the old name for this anvil-like structure that you see. So it's a very very adequate name, and so I think the people who found it were very smarter than the original D-Train team to find names. Anyway, this is a very fast happening because the launch is planned for 26. So we are having the kickoff meeting of the mission led by Sue van den Iver at CSU and my colleague Ziad Haddad from JPL last month. And the first science meeting has not yet even taken place. It will take place in October. So that's real-time information on the new mission that are going to help us to better constrain those vertical velocity computation. So this vertical velocity constraint is so important to us that on the top of INCUS, we were also having this very active program called AOS by NASA, who is now becoming an international program with JAXA and CNES, the French agency, joining in. And so we have been thinking on this kind of concept together with the same team as INCUS, more or less, but from a passive microwave perspective rather than an active radar perspective. And so a few years ago, we were able to submit to the CNES Science Prospective Seminar a proposition for what we call a COMODO, that stands for Convective Core Observations through Microwave Derivative in the Tropics. And it has been since then being involved in the design of AOS. As you can see, there's a little French flag here on the very ambitious program, but I'm not going to go into detail too much. So we are now crossing our finger for a phase B decision in mid-23. So that will really, we are almost at the end of the phase A, at least in the French sense of the phase A, but we are now reviewing all the technicalities and the cost of the instrument to really be ready for the big review that will take place in early next year for us to be selected fully. And so the PI of that project is my colleague Hélène Brognier, who is in Paris in Atmos. And again, the deadline is pretty tight. It's launched in 28 expected. And if you have more interest in this COMODO mission, I would just encourage you to go and read that paper that I highlighted that just came out last month or 2 months ago, where we are presenting the mission and some early result on the retrieval that we expect to reach from those two from this tandem of time-delayed microwave observation of tropical deep convection. So that's my last slide. I hope I'm on time. Yeah, I'm a little over, but it should be okay. We have a very physically sound framework analysis. I wanted really to emphasize that after my discussion with Michael on how we can showcase the activity going on in the climate change science and the physics of the climate change science community. It has roots in a very early pioneering work of Manabe, which is very nice that he's been recognized for that lastly. Based on those kind of theory, we can start to bring an observational constraint on those. And we are about to be able to deliver such an observationally based consistent constraint on water energy cycle evolution. And not only we can work with our satellite system on the global scale, but also at the process level, where we are able to now, by synergy of multiple perspective and instrument, add constraint on the process, which is something I also wanted to highlight. And there's probably many other cases that I could have used, but those are the ones I am doing with my colleagues, so it's biased towards my own research. And I want to emphasize the fact that we are now aiming at a more direct characterization of the convective dynamics from space. And we are very happy to have such a unique space program coming ahead. And with this, I'm done. Thank you very much for your attention.
Thanks a million for this very, very interesting insight and presentation, Rémy. Incredibly interesting and comprehensive. I have, of course, a question for you after we've been meeting last week at the EUMETSAT user days. But before, I would like to ask the participants on the seminar if they have any questions to either raise their hand now or to put them into the chat. Since I do at this point in time not see neither a raised hand nor a question, so let me fire away. You've in your INCUS slide, but also the subsequent slide, you've been showing a panoply of radiometers and exactly. So this was the INCUS and the subsequent ones where you show the American and the Japanese missions. The launch date for INCUS is in a time frame where we will have the next generation not only of geostationary but also polar meteorological satellites online. So the Meteosat third generation, but also the METOP or EPS second generation, which will be launched during the coming 2 years. MTG is going to be launched end of this year. What would be your view on how to best, if you were to go to the next slide, how would you see it would be best go about trying to combine what you have, the scenario you have on the left side of your slide with the European missions that are coming up, particularly when we look at convection? Yeah,
it's a very, very good point. Actually, in the AOS effort, which is a large, there's two sets of orbit with many platforms on it, many satellites on it. It's a 1.2 billion investment. Anyway, it's the first time for me, I've been there for quite some time already in the research world, where we very much early on hear about the program of record and how to connect with what they call in the US the program of record, which is the committed operational meteorological satellites. So that's very good news, because for this one time, it's at the beginning that we are talking about how to merge the data from AOS observing system together with the operational data set. And of course, the MTG is going to be key in that area. There is a strong push by a number of my colleagues at EUMETSAT and NOAA to try to do a geo ring with the second or third generation geo, so that we can actually benefit from all those high frequency, fine scale, multispectral observation from geo in complement to that. And I think in the product list of the actual data set, a number of the level 3 and 4 are actually merged using geo. I think as far as METOP is concerned, I have less of an idea, although I think the constellation approach of GPM will be sustained in this framework, and the massive improvement of the microwave radiometer that we are going to see coming with the post-EPS is going to be very useful. Now I'm also thinking of the Copernicus CMR microwave radiometer. I think the constellation of precipitation-oriented mission is going to be sustained with a stronger contribution of Europe than so far.
Mm. Where would you put the most intense modeling effort in the near term?
So I already thought I had a lot of materials. I didn't want to push it too much, but my colleague Graham Stephens is actively and proactively trying to alert the science community that at the same time we are having this revolution of the observing system dedicated to deep convection, we are seeing the emergence of this new climate model with kilometer scale radiation at global scale. So we are going to have a very unique 10 years coming, where we'll have the tools from space and the tools from the model are going to be on par with the same ability to serve. So he is promoting something I really enjoy, but I didn't have enough time to do. So thanks for the question. We are going to enter the decade of convection because of the simultaneous effort on the modeling side and on the data side, I would say, on the space side. So it's a very exciting time for people to look at those complex situations and trying to bridge the gap, the original gap of Manabe. He was smart to not address convection, but circumvent convection. So now we need to have the full breadth of understanding. And so it's a very interesting decade to come, for sure.
Thank you. I have a question from Jean Payeux, who is asking if the traditional rain gauges are of any help in this global evaluation of precipitation fluxes.
Yeah, so we when we are making use of a full set of constellation, we're actually approaching what I would call a simulation perspective, where we are making use of anything that comes into play. So over land, most of those satellite probably do ingest at some point the high quality rain gauges. So it's not totally disconnected from the ground-based measurement, but because it's not homogeneous all over the world, especially in the tropics, and there's no data over the ocean, we tend not to emphasize it, but definitely over the dense area like the Northern America or the eastern part of the world where there's a lot of data, we do make use of those, no problem.
Wonderful, thank you very much. I don't see any further raised hand or any further question. And with that, again, Rémy, many thanks for this insight. I found that incredibly interesting and hadn't really seen that component of the atmospheric dynamics before. So thanks again for joining us. Wait a second, before I close, there's a second question coming in from Zaharia. What is the level of knowledge of the temps moyen de résidence of about 9.5 days for, and here the is truncated. I don't see it. It's somehow got truncated. Temps moyen de résidence. I have to ask that the message gets sent before it was completed. But do you know what is meant here?
Time of residence of what?
Yeah, it seems that the message got truncated, so we didn't get the full question. Can you see it, Rémy?
No, I don't see I haven't seen
the chat. What is the level of knowledge of the temps moyen de résidence of about 9.5 days for?
For what?
I don't know.
J'ai peut-être mal posé ma question. Et bon, je suis ingénieur en retraite et je suis un peu en dehors de ma zone de confort. Je pense qu'il y a une lame d'eau équivalente de l'ordre de 28 mm de vapeur d'eau et que son temps de résidence moyen est de 9,5 jours et que ceci est un élément important du budget global, quoi. Il s'agit d'un poste qui correspond, je crois, aux 78 watts par mètre carré que vous avez montré par ailleurs. Je voudrais savoir quel est le degré de connaissance de la variabilité de ce terme de 78 watts par mètre carré et qui correspond à la durée de 9,5 jours. Pardonnez-moi.
Okay. Maybe I should rephrase it in French, in English, because it will be easier. So the idea is how do we, how accurate or how much do we have a good understanding on the water amount on the global precipitation? So actually, the answer is almost in the slide I shown. It remains one of the less constrained data, the precip compared to the other. But at this stage, it is consistent with the radiation budget. So it's good enough so that within the uncertainty of the estimation and the knowledge, as we call it, we are consistent with the surface radiation budget, which comes from a totally different perspective, different instrument. So because of that, we are thinking that we are not very far away from the truth. although we are very much now thinking in terms of uncertainty. So any improvement that will help us to go from 10% uncertainty, which seems to be fine enough for this kind of global closure. If we want to go down to more regional scale, we may want to have a finer, a more accurate data set. And so anything that is going to help us to go from 10% uncertainty to 5 will be welcome. But maybe it will be a surprise. Maybe because we will get a better understanding of the sensible heat flux or the evaporation that will put a stronger constraint on precip at the surface. So this is the funny part of this consistency approach and this very integrated, physically based view of the water energy cycle. Everything is connected. So I have good hope that in the coming years or decade, given all the nice programmatic ahead, both from the research and the operational world, these constraints are going to, the uncertainty are going to be nailed down. But when you look at the variability of the precip or the trend of the precip and the trend of the, which is not the absolute value, then it's very consistent with radiation very much.
Right.
Merci beaucoup. Merci beaucoup pour cet exposé.
There is a final question I have from Mark Sargent, my colleague at EC, our science plan manager. Which technical or scientific considerations led you to set the specific value of the time lag between the different satellites of the triple satellite formation on slide 24, which is, the Incus,
So it's actually a very, very good question. And because it's new space, the answer is different from what I would have said. We are going to adjust real time because we have no experience. So we don't know if 120 seconds is good or it's too much or too less. So the plan is to have a first 3 months row with this configuration and then do a very real-time analysis of whether or not the noise that we get in the data is good enough with respect to the signal we search for. And then we are going to adjust this 30-second, 90-second time step to better fit the scientific requirements. So it's an evolving system, which I think is very new to us to be able to go beyond a very hard fixed configuration to much more flexibility. So the true response is we'll start like this and we will adjust as during the life cycle of the mission, which is about 3 years. I hope this answered the question.
Yeah, it does definitely, and it's a good approach. I actually remember that we were in similar situations when we had NVSAT, where we had programmability of some, this was optical instruments, band sets, and we used the commissioning phase in flight to adjust as far as programmability allowed us to change the settings of the sensor. And with orbits, you have a certain flexibility there as well. Yes. Well, again, thank you very, very much, Rémy, for this most interesting seminar. And good luck with all your new endeavors. We will stay connected, Lagos and EC, I'm sure, and I'm looking much forward to learning more about the energy and water cycle through you and your work and your team at Lagos in the future. And with that, I thank you again very much for this presentation. And I would wish everybody on the seminar call a nice evening. Thanks a million, and with herewith adjourned. Bye-bye.
Thank you very much.